And action. Okay, so what we want to look at, okay, we've looked at dot product. Now here's what you want to remember. One of the things you want to remember, a dot product doesn't give you a vector, it gives you a scalar. So we have a couple of things. We have this, which gives you a scalar. And now what we're going to look at today is this, U cross V, like this. It said, we'll say U cross V. So here is U dot V, and here's U cross V. Now, U cross V is going to give you a vector. So we have a couple of things that we kind of think of as multiplication. We have the dot product, which gives you a scalar, the cross product that gives you a vector. Now, what I want to do is I want to develop this idea of the cross product by, first of all, just looking at a couple of vectors here. Let's look at this U. And I'll say here's U1, U2, and U3. And then I'm going to look at another vector V, V1, V2, and V3. So I'm just looking at some vectors, just general vectors here with these scalars inside. And here's what I want to do. I want to say that if I dot product these two vectors, I'm going to get this vector. No, I'm going to say I'm going to get 0. Sorry about that, 0. Okay. Actually, that's not exactly what I want to do here. Here's what I want to do here. I'm not saying these vectors are orthogonal to each other. I'm saying there exists a vector out there. There exists a vector such that this is true. U dot W is equal to 0, and V dot W is equal to 0. Now, what that means is I'm looking for this vector, this W, that is orthogonal to both U and V. So I've got two general vectors here, U and V, and I want to find me a vector that's orthogonal to both of them. Now remember, orthogonal means perpendicular, but when we're talking about vectors, usually we refer to as orthogonal. So I want to find these vectors. Now, here's how I'm going to do it. I'm going to do it algebraically, and it's important. So we're developing this notion of cross product, and from the very beginning, we're doing so by assuming that U is orthogonal to W and V is orthogonal to W. And in fact, we're going to say that W is the cross product. Okay? So W is this cross product. It's the vector that's orthogonal to both, and that's how we're going to define what a cross product is. So let's just take a look at this. First of all, let's look at U dot W. If you find U dot W, what you're going to have is U1, W1 plus U2, W2 plus U3, W3, and we're saying that equals 0. Now I can do the same thing for this one right here. I can say V1, W1 plus V2, W2 plus V3, W3, and that also has to equal 0. So what we have here is a lovely system of equations. And all we have to do is solve it, right? Okay. Solve for what, you might say? There's a lot of stuff going on in here. Well, I'm trying to solve for W1, W2, and W3. That's what I'm trying to do. But I only have two equations. I have 3 unknowns, so that maybe poses a problem. Part of the reason I'm developing this way is so you can just see some algebra at work, just some different algebra than maybe you're used to. Here's what I want to do. I want to, first of all, just eliminate the W3. And the way I'm going to eliminate the W3 is I'm going to start off by multiplying this first equation by V3. So, dig this. Here I go. I've got U1, W1, V3 plus U2, W2, V3. And then I've got U3, W3, V3. Okay? And of course equals 0. I multiplied both sides by that. So I've not hurt anyone by doing that. I just multiplied through by a scalar. And everybody knows you can do that. Now, on this one down here, what I'm going to do is I'm going to multiply through by a negative U3. So here's what I've got. I've got negative V1, W1, U3. Huh? Okay. Did I mess up? Oh, okay. Now, here's U2, W. Let me see here. I got to be careful not to look at this second one. I have to look at this. So here's V1, W1, U3. Okay. Now, I start to mess up here. Okay, so here's V2, W2, U3, right? Minus V3, W3, U3 equals 0. Okay. Okay, now, I'm going to add these bad boys. So we're kind of using, we are using the elimination method. So I want to add these and see what I come up with. Now, you notice right here, I've got U3, V3, and W3, a minus here and a plus. So this one is a minus, this one's a plus. Those are going to cancel out. And here's what I'm going to get. I'm going to get this. Just look at this. I've got U1, V3, minus V1, U3, W1, right? I factored out the W1 here, right? So I kind of skipped a step. I took this one and added it to this one, and I got this. And I just factored out the W1. Now, I want to do the same thing over here. I've got U2, V3, minus V2, U3, and I'll just factor out the W2. Yeah, that's it. Now, this is what I have. Okay. Now, does everybody follow what I did so far? What I've done is I've eliminated one of the variables. Okay? I've just eliminated one of the variables. Okay. Now, I've eliminated the W3. Okay. Now, let's do this. I've got this equation here. And what if I do this? What if I say this? What if I say, well, let's let W1 equal U2 V3 minus V2 U3. Why don't I, if I say that, okay, and then if I say this, I say, and let W2 equal the opposite of this one. Okay, what if I do that? Is that a solution? Okay, so this is a solution that works. Now, what I want to do is go back up here to the original equation. Okay, I want to go back up here to this thing. Whoops, here we go. And I'll just pick either one of those, okay? And I'm going to substitute back in. That's what I'm going to do. So I'm going to put in W1 and W2, and then I'm going to solve for W3. That's what I'm going to do, okay? So, and we're almost done here. So here's what I've got. I've got U1. Now I'm going to put in the solution. Now, let me know if I make a mistake here because it's very important. So I've got U1, W1, okay, plus U2, and now W2, right, which is this thing. All these negatives are maddening, okay? But there's U2, W2. Let me make sure I got that right. U2, W2, right? And now U3, W3. And that is supposed to equal 0. Here we go. Now, let's see what's going to happen here, okay? If I go through this now, dig this. I've got U1, U2, V3 minus U1 V2 U3. Okay? I just cleared my parentheses there. That's like a preschool algebra. And then, okay, over here, we have to be careful. If I distribute through here, okay, this is what I'm going to get. I'm going to get a minus U1 U2 V3, right? That's a minus. This is going to be a plus U2 U3 V1. Okay, I think I successfully got past this treacherous area, right? Because this minus makes a plus over here, so I think we got through that. Plus U3 W3 equals 0. Okay, now let's see if anything happens to make this a little simpler. Let me get the old Cavendish here. U1, U2, V3. Okay, we got that. Yay! Excellent. Now, does anything else? No, nothing else. Nothing else does. Now, we can divide out the U3, right? Okay, let's divide out the U3, and let's see what we've got over here. Okay, if I divide out the U3, I've got negative U1 V2 minus, no, plus, let me get rid of that. Okay, plus U2 V1 plus W3 equals 0, right? Did I make any mistakes there? Okay, now I can solve for W3. We have just found our vector. Yes? Okay, now we have just about found our vector because look at this. We're saying that W3 is equal to this. It's equal to U1 V2 minus U2 V1. Really? I can't believe it, but I have just found a vector W that's orthogonal to both, haven't I? Because I know what W1 is, I know what W2 is, and I know what W3 is. So I have found the cross product of those two vectors. We said we want a vector that's orthogonal to all three. I've got W, let's look at this real quick. I've got W1, which is U2, let me see, U2 V3. Okay, so here goes W. U2 V3 minus V2 U3, comma, okay, what is U2? U2 is this thing, right? Now let me swap this around, okay? I'm going to say V1 U3, or let me not do that. Let me just keep the minus out here, okay? I'll just keep the minus out. U1 V3, and what was the rest of it in there? Minus V1 U3. Okay? Now, comma. So look, I got W1, W2. Now, W3 is this bad boy right here, which is, I don't need the parentheses. Don't need it. U1 V2 minus U2 V1. That is the cross product. And what we have here is we have a vector, W, that's orthogonal to both vectors. Okay? Now, we're going to see why that's important. Okay. Okay. Now, this is the formula for cross product right here. Now, this is what we have to know. But you might think, this is kind of cumbersome to memorize. How can I ever memorize this long cross product thing? Well, there's a trick that we can use, and we're going to use this quite a lot throughout the course. We're going to use something that's like the determinant. And the determinant goes like this. Here's the way it goes. We have the I, the J, and the K. Okay? The I, the J, and the K. And what I do is I put in the vector components. Here I put in U1, U2, and U3, and then V1, V2, and V3. And what we're doing is we're using the same. Now, this is how I never memorized this right here, this formula. But this right here is probably in pre-cal you saw determinants. Do y'all remember determinants? Okay, well here's how determinants go. What you do is we're going to calculate the determinant along this first row, and here's what happens. I'm going to take this I vector, okay? And what we do is we take the row and the column that the I is on and we eliminate it. So in other words, I'm going to eliminate this and this. And what I'm going to do is I'm going to go back. Now let me erase that. Then what I'm going to do is I'm going to take these numbers right here and watch carefully what I'm going to do. U2 V3 minus, okay, so I go this way, minus this, V2 U3, okay? Then, now with these determinants, you're going to have alternating signs. So the next thing is going to be a minus. Now, at this point, let's just pause a moment. You notice we have the I component of this vector, W. And if you look up here, it's U2 V3 right there minus V2 U3. Ah, that's that first component. Now, dig the second component. It's going to be a J. Okay? Now I'm going to eliminate, here's what I'm going to do. I'm going to eliminate this, and I'm going to use these ones, right? U1 V3 minus V1 U3. Okay? So let's do this. Now, I open my parentheses, and I take U1 V3 minus V1 U3. Okay? Now, if you look up here, here's U1 V3 minus V1 U3. See, it's the same, isn't it? Okay? Now, finally, we're down to the last part, the young k here. Now, you know how this game is played. I eliminate the third column and the first row, and I get this. I get U1 V2 minus V1 U2. And there is your cross product. You can also call it vector product. Okay. So there is your cross product. Any questions about that? Okay. Now, so let's see how we would use this in practice. Let's just see how we could deal with this. Let's suppose I've got a couple of vectors. Let's suppose I've got 2, 1, and 5, something like that. And then I've got V is equal to 1, 3, and 2, something like that. If we want to get the cross product of those two vectors, we're going to, go through this process. Now, you can remember, if you want to, you can memorize the cross product, the initial. You can memorize this if you want. But most people, I don't think, do that. We use this determinant method. Okay, so look at that. Now I go through the process here, and I'm going to get a nice vector. I'm going to get this. So this is U cross V. Now order matters on these. U cross V is different than V cross U. It's exhausting? You're getting a little sore? I know. Okay, so let's do this U cross V. Okay, so what you want to do is maybe you can throw off all the method for getting here and just say, okay, the bottom line is I've got to calculate the cross product. Okay, so that's what you want to take away from this whole section. How do you calculate the cross product? Well, it's going to be I, and here we go. It's going to be 2 minus 15 minus J. Okay, Just take a minute and dig that. Now, I got that wrong, didn't I? So don't dig that too much. I caught myself. Thank you. So this is 2 minus, oh, it's still 2 minus 15. No, I did get it right. See, 2 minus 15. 2, there. I did get it right. I'm too hard on myself. Okay? Now, the J, okay? Now it's 4 minus 5. Okay? Now, the last part is K, and that's going to be 6 minus 1. There's your vector right there. Okay? So dig this now. This is going to be negative 13, comma, what is that, negative 1, comma, 5. And that's your vector. That vector right there, if you dot product it with either U or V, you're going to get that. Okay? Does everybody see that? Now, here's a property that I may have you verify. This is a property that I'm probably going to have you verify. I'm going to say this. U cross V is equal to the opposite of V cross U. So that's a property that you're going to need to be able to verify. Sure, you can. Okay, so Kyle called this shenanigan that I forgot this negative and that negative go together, so that's going to be a plus right here. Okay, so Kyle, remind me of that you need to get paid at the end. Everybody remind me. Okay, so we'll need to do this. We'll need to be able to verify this. And it's just, breaking it down into U1, U2, and U3, and so forth. Now also, remember this, that if you cross it with the 0 vector, what do you think you're going to get? You're going to get 0, right? Obviously, you have to, right? Okay, any questions about that? Okay, now, so right now, really, if you cut through all the stuff we said, the thing is, we were just trying to figure out how to calculate a cross product. And we did a lot of algebra just so you could see it and enjoy it. But actually, it's just calculating the cross product is what you need to be able to do at this point, and use the cross product to, verify those things. Now, a couple of things I want to show you. Let's suppose that, let me draw something here. I'll clone it here. Clone. Whoops. Hang on. Let me bring this over here and clone. This right here is a trapezoid. I mean, not a trapezoid, but a parallelogram. Okay? This is a parallelogram, and I've got it here on the board, of course, but it could be out here anywhere in space. Okay? So it's not necessarily, we're looking at it flat, but what you have is you have a U and a V here. Okay? So what you have is you have two vectors. Okay? You have the U vector and the V vector. Okay? Now, we could say, okay, those serve as like the sides of a parallelogram. Okay? Now, here's what I want to do. Remember that if we, what we can do with a parallelogram, we could drop a height down here, and that doesn't hurt anybody, right? There's a height. Now, then I can do this. I can take note of that this right here is theta. This is the angle between those two vectors, right? It's the angle between those two vectors. Now, let me label this as height. Okay. Now, the length of this vector here is the magnitude of U. The length of this vector here is the magnitude of V. We can all agree with that. So now we actually have a parallelogram, and we know the lengths of two of the sides. Now, I want to do this. this, if you look at this theta right here, I could say that the sine of theta is equal to h over the magnitude of v, right? I could say that. Okay. Okay, does everybody agree? Didn't do anything untoward there. Now I can solve for h, and I get h is equal to the magnitude of v times the sine of theta. And remember, theta is the angle between those two vectors. Okay, now, what is the area of this parallelogram? What do you think? What do you think is the area of this parallelogram? Do y'all remember how to calculate the area of a parallelogram? It's the base times height. Okay, here's the base, right? Here's the height, which is perpendicular to it. So it looks like the area of this parallelogram is going to be, well, this. It looks like it's going to be this. This right here is the area of that parallelogram. For sure. That's what it is. Now, here's something that I'm not going to do, but it's strictly algebra. You can show that this is also the area of that parallelogram. You can show that algebraically. Okay? In other words, the magnitude of the cross product of these two vectors is the area of this parallelogram. That can be shown. The only reason I don't is just because it's a ton of algebra. It's not even complicated algebra. It's just a bunch of it. And I've already given you, I've heaped a bunch of algebra. I was shoveling algebra on you all morning. So I don't think I need to do that anymore. And this is something that you can do if you want to. But what we have is we have this relationship right here. Okay? It's what? World? Okay, so here we have, here's what we need to note. That the area of a trapezoid, a parallelogram, is the magnitude of the cross product. And also, this is another very important property here, that the magnitude of the cross product is equal to the product of the magnitudes of the vectors times sine of the angle between them. That's an extremely important property that we're going to refer to. So you do need to remember this property. Okay, this is one of the things that you just need to know. Okay? Any questions about that? Now, as far as this thing with cross product, we have covered actually the core of it, what you really need. You need to know how to calculate a cross product. You need to know a couple of the properties of it, in particular this property, because we refer to this later. Okay? This property right here. So that helps you to understand. Now, there's something I want to show you that's kind of cool that I don't really care much about, and that is what happens if we have a parallelopiped. This thing, it's like a three-dimensional parallelogram, right? So we call this a parallelopiped. Now, I just want to show you, because the reason I'm showing you this is it kind of gives you an idea about how powerful the cross product is and what you can do with it. And in fact, the cross product, if you consider a parallelopiped, and you remember it's three dimensions, so that we have the base, V, and we have the W, making the base, and then we have another vector that goes up here, and we have parallel planes instead of parallel lines, right? So we have parallel planes here. What we take note of is this, that you can show that you can use cross product to actually get this area, because notice, if we've got U here, this U, we can calculate the height of this parallelepiped by projecting it onto an orthogonal vector. Look, if I get the orthogonal vector of V and W, and if I project it, in other words, if I project U onto that orthogonal vector, I've got the height. Now what happens is, if we do that, what we find is that you can get the area or the volume of this parallelepiped this way. You can take, well, it's going to work out to be that, okay? In other words, it kind of brings together the dot product and the cross product. Okay? Does everybody see that? Now, that would be the volume of this parallelepiped. Yeah, the volume. Now, it's easy to show, right? Because really, I know that the area, I know that the volume of the parallelepiped would be the base, the area of the base times the height, right? Now, what is the area of the base? It's V cross W, right? That's the area of the parallelogram. And then if I multiply it by the magnitude of the projection, right? Okay, let's just do that for fun here. What is let's do this. We're about done here, so let's just do this just for pure joy. Y'all are not going to have to do this, but let's go ahead and find the projection of this thing, V cross W, and we'll project U onto it. Okay. Well, do y'all remember how to do that projection? It's U dot V cross W, right? Divided by the magnitude of V cross W squared. Isn't that true? And then times V cross W. Isn't that's the projection, is it not? Now, what if I wanted the magnitude of this thing? The magnitude of the projection. Well, think about it. This right here is just a big fat constant, right? There's no vector in that. So if I square it and then take the square root, what I'm going to get is I'm going to get this. I'm going to get U dot V cross W just in absolute value because I square it and I take the square root of it. Down here, I'm going to get the same thing, the magnitude of V cross W squared, but then this is going to be the magnitude of V cross W. Right? Now, let's see here. I've got an extra square there, don't I? Well, let's see here. Let's see what happens. Oh, no, I'm not. This cancels with this, right? And that's the projection. Do y'all agree that this right here is the projection, the magnitude of the projection? Okay? That's the magnitude of the projection. So if I do this, if I take the base times the height, which is the magnitude of the projection, man, I don't think I've ever gone through this whole thing before, so let's hope it works out. Kind of taking a big risk here. Look at that. And this is an absolute value. There it is. There's the formula that I was talking about, right? That's the volume of the parallelepiped, right? It's pretty cool. You all see that? Are you down with that, Cato? See it? It's cool. Cool stuff. Any questions about this?